Hello, here we are for AP Physics Work Kinetic Energy Theorem homework set. We're going to run through the first problem. A crate, mass 10 kilograms, pulled up a rough incline with an initial speed of 1.5 meters per second. The pulling force is 100 newtons that pulls parallel to the incline, which makes an angle 20 degrees with the horizontal. Coefficient of friction is 0.4, and the crate's pulled through a distance of 5 meters along the ramp. Let's do our sketch and force diagram. So let's see. We're told that we have, let's see here, this ramp. We know that ramp makes a 20-degree angle with the horizontal. We have this crate. That they tell us has a mass of 10 kilograms. It's getting pulled up along the ramp. Let's see here. It has an initial speed of 1.5 meters per second. So my V naught is 1.5 meters per second. Let's see here. This rough incline. They tell you the coefficient of friction is 0.4. That's my mu. 0.4. Of course, coefficients of friction don't have any units. Let's see here. And they tell me that it's going to get drug up through a distance of 5 meters. So I might drop like a coordinate axis here and kind of go. This is my delta x. Maybe we'll say, hey, here is position 0. Here is position 5 meters. There we go. So I've dropped the coordinate axis down. All right. A force diagram. So we're going to take a look at this crate. So I might draw my diagram over here. Right, because I'm not going to draw in my original sketch. Let's see, forces. You'll say ranged forces. There's going to be gravitational, which go along the line between the center of the object and center of the Earth. I'll label that mg, right? And you say contact forces, what's touching it? Well, there's something that's pulling it, right? There's some pulling force. Let's see here. They tell you that's 100 newtons. That's that. What should we call that? F sub P, I guess, for pulling force. Why not? Okay, that we know is 100 newtons. Okay, that's going to show up on my force diagram like so. Let's see here. What else do we know? Well, the only other thing touching the box is the ramp. And so you ask the questions, are they being pressed together? And then are they trying to slide past each other? They are being pressed together. Gravity shoves it into the ramp. So the ramp pushes back with a normal force. That's got to go perpendicular to the surface. Once you have a normal force, there's a chance of having a friction force. So you ask, are those surfaces trying to slide past each other? You say, yes, it's sliding along the ramp uphill. So the friction force is going to go downhill. There is my kinetic friction force on the box by the ramp. And that's my force diagram. Let's talk coordinate axes. We know that we always make our first axis go along the direction of motion. So my coordinate axes are going to go parallel to the ramp and perpendicular to the ramp. And with energy, we know that when we're calculating work, we care about the component of force along the motion, right? And so we really want to do our coordinate axes along the direction of motion. Let's see, I usually call these the parallel to the ramp and perpendicular to the ramp directions, and call that way positive. Hey, what force has to get split into components? Just the gravitational force. Perpendicular to the ramp. Parallel to the ramp. Of course, the 90 degrees between the components. We are going, again, into the ramp and downhill are the ways that gravity is pushing. And we know if 20 degrees is this angle, the ramp makes it horizontal, then that is this upper angle here is the 20 degrees, making this mg cosine 20 and mg sine 20. And that is my force diagram done. Okay, so that was part A. We got our sketch, we got our force diagram. Let's see here, part B, they want to know how much work gravity is doing. Essentially what we're doing here is, in this problem, I'm kind of taking this problem where we're trying to find the speed of the crate after it's gone through those 5 meters. And I'm taking the calculation that you would do to solve for that and kind of breaking it up into chunks for you here. But you know what? I'm just going to do it all in one big one big go. The way I would normally do if I was trying to find the speed of the crate, I'm just going to do the whole thing, and we'll talk about it as we do each chunk of the calculation. We'll talk about which part we're doing. So here we go. So in general, the approach for doing these problems, we're going to go right for solving for what's the speed of the crate after it's been pulled 5 meters. We remember that the big formula for energy is this one. All right, the work energy theorem. Specifically, we are ignoring potential energy for right now. So our work is going to be going towards changing the kinetic energy of the system, right? Anytime you do a work calculation, we're always talking about doing work, forces doing work as we go from this position to this position. We're talking about changes in energy as we go from this position to this position. Point is, there's always a start and an end. I like to mark those on my sketch so I keep track. I'm going from here to here, right? Pretty straightforward in this problem. And so I'm looking at what forces are acting as I go along from here to here to figure out what work terms I have. Every force that acts on my system, I can write a work term for, all right? So what I'm going to do is I'm going to expand this sigma W out into this work plus this work plus this work plus this work for every force. And so that's going to look like this. I might have a work done by the gravitational force. Plus, I'll have work done by the friction force. And I might have work done by that pulling force. I might have work done by the normal force. 4 forces, 4 work terms. On the right side of the equation, that delta K, I can expand that out. Delta is a final minus initial. So I might expand that out to be the final kinetic energy minus the initial kinetic energy, okay? These are capital Ks, not lowercase ks. Lowercase k is going to show up very soon as the spring constant. So be careful about what Ks you're doing because we're going to have spring constants running around our equations eventually once we have springs involved. And so we'll have, well, you get it. So make sure your Ks are clear, capital versus lowercase. Alrighty, moving onward, kind of like that mu looking different than my M is important. Okay, okay, now we're going to go ahead and each of these work terms I can go ahead and analyze. Now, we remember that in order to do work, a force has to be pushing along the direction of motion. Pushing with the motion means that force is pumping more energy into the system, doing positive work. Pushing against the motion, it's trying to slow the system down, doing negative work, reducing the kinetic energy of the system. If a force only pushes perpendicular to the motion, well, then that's not helping it to get any faster or slower. It's not doing any work. So right away, if we just by inspection, you might glance at this and say, look, this normal force, it's perpendicular to the motion, right? It's at a right angle to it. It's not helping to push it faster or push it slower. So I recognize that this term is going to drop right out of my calculation because that normal force is perpendicular to the motion, okay? And so I recognize that's going to drop out and be no work. So I could spot that right away. In this case, we're moving at the start, so we do have some kinetic energy at the start. And at the end, we're trying to find that final velocity. We're going to be moving at the end. So none of the rest of these terms are going to drop out. I'm going to have 1, 2, 3, 4, 5 terms in my equation, actually, in this case. Right? Oftentimes, we're looking at something that starts at rest or comes to rest, and so the kinetic energy terms will drop out too. But no such luck this time. We've got 1, 2, 3, 4, 5. Alrighty, let's work through them now. Work. We have a formula for work, and that is that work is the integral of f dot dx. So I'm just going to jot off to the side here. Work. It's the integral of f dot dx. All right. And so officially, each of these I'd be writing a little integral for. So I would have my integral of the gravitational force dotted with the dx, right? Little bits. And what I'm doing here is I'm adding up the work that gravity does as I move along, this little bit, this little bit, this little bit, as I'm moving along this distance, splitting a bunch of little dx's, looking at the work done here, work done here, work done here, work done here, as I push through each little bit, adding up, that's the integral, adding up this force through distance as I go along. Technically, I'm doing it from, here's my variable of integration, from x equals 2x equals. So I'm going from x equals 0 up through x equals 5. So I would have bounds here on my integral, bounds. So it's a definite integral. We're going from x is 0 to x is 5. All right. I would add to, should I go ahead and fill in all the rest of the terms? Oh, sure, real quick. I'll go real quick with the rest of these. I'm going to do an integral from x is 0 to x is 5 of the friction force dot dx. And I'd have an integral from x is 0 to x is 5 of that pushing force dot dx equals, on the other side, if I wanted to, I could plug in 1/2 mv final squared, use that kinetic energy formula. That kinetic energy is 1/2 mv squared, right? And substitute that in here. I'll substitute using the final velocity for this term and using the initial velocity for this term. I'm going to come back and do that later. There's no rush. I'm going to have to do a bunch of calculations here first. So let's work through this now. Let's go through each of these terms. The next thing I like to look at is I like to take care of that dot, okay? Because that dot product's really weird, right? We remember that what that dot product means. It means we're going to take the absolute value of this times the absolute value of this times the cosine of the angle between them. Okay, because I'm getting basically, I like to think of it as taking just the part of the force, the component of the force that's parallel to the motion. Just play along with me here. So when I do this, it's going to be mg times dx times the cosine of the angle between them. You say, well, what is the angle between the gravitational force and that dx? What is going to be the cosine theta that's going to get substituted in there? You say, well, what I want specifically here, that cosine theta, it's not the angle of the hill. That's not what we mean. This is the angle between this angle here, this cosine theta there, here, integral of f, absolute value, cosine theta, absolute value dx. Okay, that's what we're doing when we do this dot product, right? This angle is specifically whatever the angle is between the way the force is pushing and the way the object's moving, right? That change in position, the way it's moving. So in this case, what's the angle between the gravitational force and the motion along the hill? You say, well, look, do you see here the motion is parallel to the ramp? Here, right here, this is in 90 degrees, and then we go another 20 degrees. This is 110 degrees is the angle between the way we're moving and the way the force is pushing. So this should be, I'm going to be putting into there a cosine of 110 degrees. All right. By the way, the cosine of 110 degrees, is that positive or negative? You say, I recognize 110 degrees, that's like a quadrant 2 angle. You say that's going to be a negative cosine. And that's okay. That's what we want. Because gravity is fighting against the motion, trying to slow it down, isn't it? It's trying to pull downhill while we're moving uphill. And so this should be a negative work term. Gravity is trying to take kinetic energy away from our system, trying to slow it down, right? Okay, so we do want that term to be negative, and that cosine is going to take care of it. That's why everything else we do absolute value. So the only plus or minus sign is from the cosine functions. That takes care of direction, takes care of the sign, direction that we're moving compared to the direction of the force, and that's what determines the sign on the work. Okay, so good enough. So this is going to turn into, I'm just going to continue down with this one, and we're going to resolve this term first, just because of the way the questions are on the homework set. They ask you first about the work done by gravity. But what I realize now is this. Hey, once I put that in there, as I move along, is the mass going to be changing as I go from x equals 0 to x equals 5? You say, no, the mass is constant. What about g? You say, well, that's a constant. What about that angle between the force of gravity and the motion? As we move along the ramp, you say, no, that angle's staying the same between gravity and the... So in other words, all these things are constants. The m, the g, the cosine 110. When you take an integral, things that are constant can factor out of the integral. So when I do that, I'm going to get m and g, and yeah, technically there's an absolute value on those, and cosine of 110. What's left inside the integral? Well, it just looks like this. Integral of dx from 0 to 5. If I add up, I'm taking this path that I'm going along from x is 0 to x is 5, and I'm splitting up into a bunch of little dx, 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 dx as I go along. If I split them a bunch of dx, if I add up all those little changes in position, that's the way we like to think about it in physics, little changes in position, aren't they just going to add up to just be that total delta x, right? They're just going to be that displacement. This is just delta x. So what this is turning into, right? Technically, you say, this is like I'm taking the integral of 1 dx, don't you think? What would give me 1 as its derivative? Well, that would be x, right? Derivative of x would be 1, right? And you say, hey, and I evaluate that from 0 to 5. I'll put the final minus the initial. That would just be 5 minus 0. But you know what that is? That's just the final x minus the starting x. That's just delta x. That's what this is. This whole chunk is just the delta x. It's just the displacement. All right? So what this turns into then, right? Technically, I've got my absolute values and absolute values, right? This is just the absolute value delta. This is just turning into this equation. Absolute value of force, cosine of the angle, absolute value of the delta x of the displacement. That's just this formula that you remember from last year. This formula from last year is a special case formula. It's a special case of the real work formula here. It's a special case for if the force is constant and that angle there between the force and the motion is constant. Then you can use the simpler version, right? Really, it's just a special case of this formula. In this case, we can just use this because the force and the angle were constant. And so you say, so this is a case where I could get away with just using the simple version. Students ask me sometimes, hey, when do I have to use the integral form of work, and when can I get away with using the old version from last year? And the answer is technically, we always use the integral form. It's just, it simplifies down to become this with a constant force and angle between the force and motion. All right. So this is really just going to turn into mg cosine 110 times delta x. Do I want to write it that way? Yeah, I'm going to go ahead and do that. mg cosine 110 delta x. And I know that the mg is going to be positives and delta x is going to be positive. And so the only sign is from the cosine. It's going to be negative. This will become a negative for me. Everything's going to work out great. Okay, let's go to the next term. I could put the values in and get the answer for the question in the blank, but all right, fine. We'll do it. Hey, I know what the mass is 10 kilograms. G is 9.8. Cosine of 110 times my delta x of 5 meters. And you say, okay, 50 times 9.8 times the cosine of 110. And my calculator spits out that this is negative 167 point, I'm going to round it off, 6. The units on work, it's force times distance, so it's going to be Newton meters, but it's also an energy unit. So you can call it Newton meters, or you can call it just joules. That's energy, that's fine. Okay, let's go to the next term. Okay, let's find the work done by the friction force. Now, the way they asked the question was they asked how much energy is lost due to friction. That would be how much energy is removed from the system by the friction force. Well, you know what that is? That's energy leaving the system. That's work. That's just asking you what the work is due to friction. And just being nice, pointing out to you that energy is leaving the system. Not that you needed to be told that. You say that friction force is going against the motion. It's going to be slowing it down. If I did my little calculation here, you would say, hey, that angle between the friction force and the motion, that's going to be 180. It's going to be a cosine of 180 degrees, right? It's going opposite the motion. And you say, well, gosh, cosine of 180, that's just -1, isn't it? And so that's going to make this term negative, which is what we want. We want that work done by friction to be negative. Is the friction force, that kinetic friction, going to be changing as we move along? No, it's a constant. It can kick out of the integral, right? And then that angle, is that going to be changing? No, friction's going to be going against the motion the whole time. It's going to be cosine 180 the whole time. That's not changing, right? So that can also, it's a constant. It can also come out of the integral. And then I'm just left with the integral of dx. That's just delta x. Once again, this is another case that reduces down to that simple form of the equation from last year. All right. Let's see here. Just doing the math now. You say, well, actually, friction, they didn't tell me the force of friction. They told me the coefficient. So I'm going to use my friction formula. That friction is mu times n, right? I'm going to stop color coding here. I'm just going to kind of crank through this. The cosine 180, I should just start putting a -1 there, right? Okay, next step. Hey, normal force, how big is it? If I did my sigma f in the perpendicular direction, I'm just going to skip ahead because this is second year physics. We know that normal force is going to balance out mg cosine 20. Those are the only forces in the perpendicular axis. So n is going to equal mg cosine 20. So this will be mu mg cosine 20. And then I have that cosine 180. That's just a -1. And then my delta x. Okay, let's stick our values in. 0.4. Oh, I should have switched colors here. Sorry. I was going to match what I was doing before. Sorry. This is going to be 0.4 times that mass of 10 times 9.8 times the cosine of 20 times -1 times the delta x of 5 meters. Okay, we're going along 5 meters. Okay, punch that in my calculator. 0.4 times 98 times cosine 20 times -5. And I got negative 184.2 joules. All right, so that is the amount of energy removed by friction. That friction is taking out of the system. Okay, so 184.2 joules. Okay, negative showing that it's leaving the system. All right. Okay, let's go to our next term. This is going to be the work done by that pulling force. All right. It is a constant pulling force of 100 newtons. That's a constant. The angle here between the force and the motion, hey, we're pulling along the ramp, we're moving along the ramp. That's going to be a cosine of 0 degrees, which is just +1. Okay. And so that's a constant. That's a constant. They're going to kick out, right? I'm going to have that pulling force times the cosine of 0, right? Times delta x, right? So that's going to turn into when I integrate dx. And so cranking through my numbers, let's just come on down here, right? You say, hey, that's going to be, what's my pulling force here? 100 newtons times cosine of 0 is just +1. And then my delta x of 5 meters, you say, guys, that's really easy. That's just 500 joules of work done by that pulling force. Hey, this normal force did no work because it was perpendicular. If I didn't spot that right away on my own, maybe I didn't see it. I was just kind of cranking through writing work terms for all my force. I didn't notice right away. You notice what would happen here when I went to do the f dot dx here, the angle between the normal and the motion would have been 90 degrees. And if I punched in my calculator cosine of 90, it would have told me 0. And so the formula will take care of it. If you didn't spot it right away, you would get a cosine of 90, which would be 0. And so you would have nothing, no work being done by that normal force as it goes along the ramp. Will a normal force always do no work? No. You can imagine having, here is my plate with remains from a yummy, delicious pizza I had. If I see this knife, gravity pulls down on it. Normal force on the plate pushes up. What happens if I accelerate the plate up? Isn't that normal force pushing up on the knife going to be bigger than the gravitational force? And that normal force is going to be doing work, pushing in the direction of motion, making that knife speed up, that force from the plate. So you can have a normal force that's doing work. Don't think the normal force is always going to be perpendicular to the motion. It always sticks out of a surface, but it doesn't mean the normal force doesn't do work. All right. Getting back to this. Hey, the right side is just that change in kinetic energy. Yeah. That right side is just the change in kinetic energy. Okay, good enough. Hey, can we calculate what the change in kinetic energy was? You see, yeah, just go ahead and add this up, right? So I'm going to have, let's see here, minus 167.6 minus 184.2 plus 500. My calculator tells me, hey, that change in energy is around 148.2 joules is the delta K. All right. Notice I'm getting a positive. Look, the amount of work put in by that pushing force is bigger than the amount of energy taken out, right, by those other two forces, by friction and gravity. And so overall, this is gaining kinetic energy. That block is going to be moving faster and faster. That crate, as it goes up the hill, is going to be getting faster. We're expecting our final velocity to come out to be bigger than 1.5 meters per second. All right. Hey, where are we at now? We answered this and this and this and this. We're ready to go to the last part. Find the speed of the crate. Well, this is equal to the changing kinetic energy, right? I'm just going to come over here and give myself some space. 148.2, that's going to be equal to K final minus K initial. That's going to be equal to 1/2 m, plugging in the kinetic energy equation, using the final velocity for the final kinetic and the initial velocity for the initial kinetic. Hey, you know what? I'm trying to find this final velocity. I know the mass of the crate is 10 kilograms. I know the starting velocity is 1.5. I know everything I need to know to solve for that VF. I can just put my values in and solve. In fact, I could factor out the 1/2 m and make my life easier, right? Maybe that would make it easier. I don't know. Is it going to make it easier? I don't know. Minus that 1.5 squared, right? Anyway, so I'll do the calculation. You say, yeah, I'll take that 148.2. I'll multiply by 2, divide by 10. Times 2 divided by 10. And that's equal to VF squared minus V naught squared. So I'll add the 1.5 squared over to the other side. And that's the square of the final velocity. I took a square root of that answer. Bam! And I'm getting that my V final ends up being 5.65 meters per second. Ta-da! And that's that problem. So, yeah, there's a whole lot going on in this problem. The biggest things about it is just going through an energy calculation, which you should have done last spring. But in particular, looking at it kind of from this point of view, recognizing that sometimes if we have constant forces and constant angles, this new version, right, the real version of the work equation will simplify down to be that simpler version from last year. And that's fine. Good enough. Okay, being careful about our signs. The only sign is from the cosine. Yeah, everything works out. Okay, that's it for problem 1. Right, I probably should have numbered that. This is problem 1. Okay.